We continue our heterogeneous computer discussion with PhD candidate Michael Robson. We'll be discussing heterogeneous computing using the GPU manager and, in fact, more than just the GPU manager.
Cool.
Looking at more than one platform.
Yeah. Thanks, Eric. So as you said, I'm Mike Robson. I'm here today to talk to you generally about heterogeneous computing in Charm++, PhD student in PPL. So before we go any further, just to clarify, when I say heterogeneous computing, I'm specifically talking about, especially in this talk, GPUs, and specifically NVIDIA GPUs. So Charm does work on the Xeon Phis. It does work on cells. At least we have older versions that work there. But for this case, we're talking about just NVIDIA GPUs, and specifically ones programmed with CUDA. So for modern NVIDIA GPUs, if you're familiar with them, you know they have thousands of threads, so there's a lot of parallelism you need to expose to use them fully. They have a lot of memory bandwidth, but not so much memory on the card themselves, and they have a lot of double precision floating point performance. So these sort of unique number crunching machines have to be used in different ways in order to get the best performance. They're very different from a regular CPU. All right, so first thing to talk about Charm when you're talking about GPUs is GPU Manager. And this work was really done with, or some of this more recent work was done with a new student in PPL, Jamin Choi, who provided a lot of this. So GPU Manager is our GPU task management library. So basically the way it works is you can register a kernel for asynchronous invocation with the runtime. And this is nice because basically you can continue doing your CPU work once you've registered this kernel. The Charm runtime will launch it when the data is ready. You can overlap the GPU work with the CPU work. You can also automate the data movement. So again, you describe what data is going to be moved. Charm runtime will move it for you, launch the kernel once it's ready, and then return to you control once it's finished all the calculations. So this leads to some really nice overlap, and I'll show you a couple slides that demonstrate that in a little bit. For both execution and data transfer, so anything that's going to the GPU, you'll be copying data in, copying data out, and executing, all the while potentially executing work on the CPU, so you can get a lot of overlap of parallelism there. Another nice thing that the GPU Manager provides is a pre-allocated pool of pinned memory. So if you've worked with GPUs before, you know pinned memory is page lock memory that you can do asynchronous data transfers out of. This is important because you want really fast asynchronous transfers to the GPU. You want to take advantage of that memory bandwidth. Move as much data as you can to take advantage of that performance. And if you pin memory, it can potentially block all of the streams you're executing, depending on how you do it. So we provide you a pool up front that you can take advantage of and just have your data already in there ready to go. We also integrate tightly with runtime profiling available in Charm, which is projection. So I think Tom did a great job of demonstrating the utility of that tool in his talk. But there's also GPU hooks, or hooks in the GPU manager that expose sort of when data gets copied or when it's executing so you can view it. And we've also done a bit of work on integrating this with NVIDIA's toolkit as well for runtime profiling, and I'll show you some results there. So to use GPU Manager, if you're interested in the audience and haven't used it yet, I would encourage you to give it a try. It's something we've been putting a lot of work into recently. So basically you build Charm with the CUDA target. So if you want to build Charm with SMP mode, you have the SMP keyword. If you want to build Charm with the GPU Manager, you have the CUDA keyword. Most things we take care of. There's a whole manual section you can read if you want to know more. And the basic process to use this is we call it enqueuing a work request. So a work request describes basically the lifetime of your GPU task. So it compromises three different things. The first one is going to be your buffers. So whatever data you need to move to or from the device, you fill out some structs that describe these buffers, how big they are, where they live, what kind of data they have in them, and then if they need to be copied to or from the device. So that's part of your work request, part number one. The second part is callbacks. So this is a little bit of stuff we added recently, but originally when your function finishes, so you kind of a regular entry method, right? You go into the function and maybe it sends some messages out and continues. Now for GPU, you have a regular GPU method you execute, and then some callback is going to be executed on the host. So this allows you to continue doing host-side work once it finishes. And now we've added the capability to do that a little more often, but I'll talk about that later. And finally, you write your run kernel function. So this is something new we've added. But basically, now whenever you want to launch a GPU application, you just write a simple function that's part of your work request that launches whatever it might be. Maybe it's a cuBLAS call, maybe it's an actual NVIDIA kernel, maybe it's some other library you want to use that takes advantage of the GPU. So you have the flexibility to launch whatever you want inside that function when the data is ready. And that will be invoked once Charm has finished copying all the data. All right, so that's how to use GPU Manager. So now I'm going to bash on GPU Manager a little bit. I inherited this code when it was made for running one kernel at a time on the GPU. So there are a couple things here that aren't the best, and I'm going to point those out. So basically, the lifetime for a GPU call kind of looked like is you would call pin malloc host, which grabbed this pin memory. This could potentially block the streams, so basically you could potentially do some work in the meantime, and then you'd eventually have a callback which says, okay, your memory is ready, now you can go ahead and use it. And so the one thing is now we have a mempool, so if you need that pin memory, you can just use the mempool memory instead, which speeds up work there. So I said that already. There's also some mem copying into these pin memory buffers to have them ready for transfers. We were working on getting rid of those as well, but they're necessary because, as we have found out many times in very painful ways, you can only pin so much memory on the host side before it blows up in your face, whether it's too many allocations, too large of an allocation, etc. And then finally, there's this handling of work requests. So it used to be a kernel select function instead of a run kernel function that was invoked anytime you wanted to run a CUDA application. It was this long, complicated switch statement, and you would fill in the block relevant for your kernel. So we've gotten rid of this as well. So we've really revamped this runtime, or this whole process basically, for how it used to work. So originally we had 3 streams for both data transfers and execution. The first, the data in stream, pretty obvious. Kernel stream, this is a stream on which the actual kernels were executed, and then a data out stream. So the way this works is that the runtime would periodically call the GPU progress function, which is basically this internal runtime function that would be invoked when there was a PE that was idle and enough time had passed, so some quanta had passed. And then it would check, okay, I have this queue of my work requests, and they're at various stages in both the data in stream or the kernel stream, and it tries to move those forward one by one. And so this would basically result that you can only have one kernel executing at a time, one kernel moving data in at a time, one kernel moving data out at a time. It also meant that we only used 3 streams and couldn't really do any higher level stuff with them. So what this kind of looked like in practice, so here's a theoretical example that we mocked up. So basically you have some CUDA malloc, you start copying data in, and then there's a gap, right? So we've started this first async, and we call it GPU progress function here. And again, this was stuck, so we couldn't do anything. And then not until we call the GPU progress function again can we start our second malloc. So that's already a problem, right? These gaps are really bad that we have to wait, right? We would ideally want to copy this memory and then do the next operation immediately. There's also the problem that we couldn't run kernels simultaneously. So if we copied the data in for the second kernel here, we couldn't execute at the same time as kernel 1, assuming, of course, they can share the resources, right? If your kernel is large enough it occupies the entire GPU or it takes too much shared memory, that might be a problem. But saying you had 2 smaller kernels, we didn't have a way for them to occupy the GPU at the same time. And this is a lot of problem because many applications have smaller kernels or kernels that don't occupy the entire GPU. So we wanted to enable this. So that was one thing we noticed and been working on. And the other thing was we couldn't have actually started this mem copy either because we would block these streams, right, for the CUDA malloc. So basically we saw a lot of problems with the old version of GPU Manager and have been working on changing them. The new design basically avoids polling via stream callbacks. So now we don't have to wait, some number of milliseconds or whatever to call the GPU progress function to check the state of the queue and move the work requests forward. Now we just say, we create a stream for every work request, put all of the operations in that stream, and then let the CUDA runtime handle all these overlap. So basically this means now that, the ordering is still the same. It'll always be copy data in, execute, copy data out. That will always still happen. But now you can run multiple kernels simultaneously. You can copy data in for a kernel while executing kernels. All that stuff still is supported. We've also added new callback locations. So originally, if you're executing a GPU code, You would copy the data in, execute the GPU code, copy the data out, and you have a callback called. And that's when you know everything is finished and you can use that data that's been copied back. Now we've inserted new locations that after the data gets copied to the GPU, if you want, you can make a callback. So say, okay, now that the data is copied, I want to continue some computation. Or, if you've started executing on the GPU and you know stuff is available to you, you can invoke a callback. So those are all new options in the new design. And we do some other stuff now. We detect the version of CUDA that's available and the hardware that's available to launch the maximum number of streams so that we can have as much concurrency exposed to the GPU as possible and run things simultaneously. So what this looks like, so I briefly mentioned that we have been working to add support for NVIDIA's tool extension library, or NVTX. So this was just a sample application that launches 4 different kernels. They're just a couple threads each. They don't really do anything interesting, but they run for a set amount of time. And in the old application, you see that the 4 kernels can't run simultaneously, even though all 4 of them could easily fit on the GPU. They're each like I think they occupy 1 SM or 2 SMs maybe. But they have to run in order because we have this in order queue that exists in GPU Manager. You also see that occasionally this GPU progress function helper is invoked here that does these CUDA frees in the background, but that's only periodically as well. And you also have regular host work here that happens. Now in the new version of GPU Manager, which we've been working on, you see that all of this work now gets overlapped. You can run still the same 4 pieces of host-side work and then overlap those with the same 4 kernels that were running before, now running on the GPU, and they're all running simultaneously. So this has been normalized so that these graph scales are roughly the same amount of time. So that's the savings you see when you use this new GPU stuff. We also provide the functionality that in case you do have kernels, say, that need to be on the same stream, they work on the same piece of data, or they're dependent for one reason or another, you can enqueue those in order such that they will still have this sort of behavior here. So that's still preserved. So we've just added new functionality. Briefly, we're going to talk about some results. So OpenAtom, which is going to have a much more extended talk later in I think tomorrow they have. Basically, it's an ab initio molecular dynamics application. I've been looking at, they have forward and backwards pair calculators, so just regular matrix multiplies. And it's been a new GPU target, so it's not been a lot of intensive work here. But basically, this is the projections timeline for OpenAtom. This is on 64 nodes of Blue Waters, XK nodes. You can kind of see what this looks like here. And we're doing multiplies basically in these green sections. And then when we offload these to the GPU, we get much better performance. So it's about a 10% reduction in time per iteration by just offloading those pairs of multiplies. So that's OpenAtom. We've also been working on Changa, which should say Changa up there. Listening to old slides. Anyway, so Tom may have beat me to the punch a bit here with his fancy GPU numbers. So I just have a small thing when he was talking about the new SMP and CUDA modes. So originally we couldn't actually get this red number down here, which is about twice as fast than the SMP version on Blue Waters. And this is just a small Dwarf 1 benchmark. Again, 4 XK nodes on Blue Waters, which is where we test stuff. But we can see we get pretty big performance jump there, about 2x, over the regular non-GPU version. And now we can actually run it with all the workers available on the nodes. This is what he was talking about earlier when you're able to scale up using SMP earlier. All right, so that was GPU Manager. That's sort of one half, more of the production ready. If you have a CUDA kernel ready to go when you want to register at the runtime and execute it, or a bunch of kernels in this case, that's what you're working on. Second half of this presentation is more focused on what we call the Excel framework, which is a bit more research and experimental, so it's not really in production yet. But basically, the motivation behind the Excel framework is that we want to use runtime information for our dynamic execution. In this case, the runtime can map to various platforms. Various platforms here means the CPU or the GPU. And it can proactively move the needed data. So if we know we're about to execute on the GPU, we can go ahead and move data there, and then execute. Also, the big motivation for this was we don't want to leave hardware sitting idle. A lot of these new supercomputers have GPUs. And they're not exactly the easiest thing to program, as I've been working on them for a while now. So we want to provide a bit of an on-ramp for people who already have existing charm code and want to experiment with GPU functions using our framework. So the way Excel works is it takes an entry method that's tagged and generates both host and device code. So this isn't anything fancy. Right now, we basically have two blocks. You write a device block and you write a host block, and it copies those into some generated CUDA kernel, and it copies it into a generated host function, and then it calls which of those ever is appropriate. You can also extend those with tuning keywords. I'm not going to go too far into that, but basically you can say how many times this is going to be called or how many threads you need, that sort of thing. And you, again, annotate the data access to the actual object. So this means, because your charm object might have data it needs to access when it's on the GPU, you need to let the Excel framework know what's going to be needed copied there to be accessed. This work also builds on top of the GPU manager. So basically, it uses the GPU manager underneath to launch all the kernels and do all the data movement. But a nice improvement it has there, and this has been mentioned a couple times in other talks, is that it actually batches together these fine-grained kernels. So one of the big problems with using GPUs, I think has been mentioned many times in previous talks, was that if I have a char, which is a very fine-grained object, trying to only do 10 threads of parallelism, that's way too much work, or not enough work for the amount of overhead it costs to launch the kernel, move the data, and copy it back. So Excel tries to tackle this problem by agglomerating tens or hundreds of these kernel launches together into a single kernel launch that all run simultaneously. So to give you an idea of what this looks like, it's a weird resolution going on here, but so you have a regular charm entry method, so entry foo, ignore this bit down here, it's a little smushed. Basically, regular charm entry method, right? Some implementation, we don't actually care what it does. So to make this an accelerated entry method, to play around with this framework, basically just add these bracketed Excel keywords. And then this will generate both the host and device versions of these. Now, I said you can also add a tuning parameter. Triggered in this case just means that every char in the array will trigger this method before it triggers it again. So this just informs the Excel framework about how it can do batching. It has an idea of how many of these are going to be sent to the GPU before another wave is going to be sent. And then I also said that you need to annotate the object access. So in this case, the char has a matrix that it owns, and we're going to read that matrix. It's of some size, it's a float, and then this is the matrix part of the object, and then same thing, we're going to write back into the temp version of that matrix that the object owns. And then at the end, and this is supposed to be now uncovered, it's kind of cropped here, but this foo post basically is the callback that gets invoked when this whole entry method finishes. So it uses that same mechanism. It's going to copy this data to the GPU. It's going to execute whatever you have in this kernel here, and then when it's finished, it's going to copy the data back, and then execute foo post, which is written elsewhere, but I left it off for brevity. That will basically, then you can resume control of your object and let you do whatever else you need to do after this computation is finished. So we have a couple benchmarks to evaluate this. We ran 2 of these.
I have a question.
Yeah?
Where's the size of the thread block specified?
The size of the thread block, where is the size of the thread block specified? Again, that's something I left out. You can actually put it in this here. I think it's block ID or thread ID, and then you can give it a number, basically. That'll say that size. That's a good question, though. Yeah, so benchmarks. We did 2 simple benchmarks. One is called Stencil 2D. It's basically Jacobi 5-point stencil. A little more CPU friendly in this case. And then Molecular Dynamics, MD, which is just supposed to be a very, very lightweight kernel that mocks up that like a mini app. We ran this on Stampede, just on a single node with a K20 and 16 cores on that node. So what you now see is a bunch of points on this graph. So basically, higher is worse in this case. So this is execution time for number of iterations for Jacobi or Stencil 2D. And then this is, as we move from left to right, we're increasing the amount of work that we send to the device. It's basically saying at the 0.5 point here, we're saying 50% of the invocations of this entry method are being sent to the GPU, and 50% are sent to the CPU. And so the Excel framework underneath batches these up, sends these as a kernel invocation, et cetera. And you can see, since this is a little more CPU friendly, we don't want to send that much work to the GPU. Anywhere between 10% and 40% is right where we want to be. Sending more and more work to the GPU, this kernel is not well tuned there, so it's going to have worse performance because we're leaving the CPU idle and using a resource it's not suited for. You see sort of the reverse behavior in the molecular dynamics or MD app, where as we go more and more towards the GPU, about 65% is the sweet spot here. You're seeing better and better performance because you're moving more and more work to the GPU. And obviously, using some of both is going to be ideal. So sort of the high-level analysis here is that, regardless of what you're doing, you're going to want to use some of each device, right? As long as you can run there, it's better to use it. Right, so using hardware improves performance. This is a no-brainer idea, but we thought it was good that might as well use both the CPU and GPU if you have them, even if it's not the greatest thing, even if it's just very straightforward, naively tuned CPU code, it's still worth using. Yeah, so those are sort of the initial results from the Excel framework there. So future work, there's a lot of it left. I only put a little bit back up. So we have a lot of things we want to tackle, versioning and code generation. So I showed you a small snippet of how the code works for CPU and GPU, but basically we're looking at writing a raw CUDA kernel directly and writing a raw CPU code directly and having those invoked correctly. We can do that right now, but we want to clean that up a little bit so it's a little more user-friendly. With the recent improvements to GPU Manager, we can now we can envision supporting OpenCL, which has a lot of the same primitives as CUDA does, so moving data, executing. So we want to enable an OpenCL mode as well. And then now we have, instead of an in-order queue, which is what GPU Manager used to be, execute kernels basically in whatever order you enqueued them. Now we want to be able to give those priorities so that if you have more important GPU work that shows up, that those can execute first. And then sort of other ongoing experiments with unified memory and multi-devices. And this sort of leads more towards our higher level goal of being able to do load balancing, right? Sort of our hallmark thing in Charm++ across a bunch of nodes heterogeneously, both CPU and GPU. And this is part of that work, and I think Ronak is going to speak more on this later about how we can balance across different dimensions and make this as performant as possible. So with all of that, I'm Michael Robson, and are there any questions?
I've got a couple of questions. So on the OpenAtom slide, did I hear you right that you got a 10% improvement for having another 300 watts on the GPU?
Yeah. Yes. Yes.
Okay.
Yeah. So that was we took like two sets of matrix multiplies and just offloaded those. So this is sort of there is a lot more that can be done in OpenAtom, but this was like the most low-hanging fruit. Like, oh, we have a matmul, let's just do cuBLAS for that sort of thing. And we're working more on that. And yeah, I know the power is a frequent criticism of GPUs. But yeah, no, that's yes. You heard me right.
Second question. So all this was targeted to GPUs. The Knight's Landing can now operate as a standalone processor, but it can also operate as a coprocessor. So can you target that in this framework?
We could probably do some weird hacky thing that did that. Right now, so the reason a lot of this stuff refers to heterogeneity is a lot of the group this came out of was interested in the cross-section of like GPUs and Knight's Landing. And really what we found in most of the experiments in Charm is the best way to run is just to run it as a separate Charm node, not to actually use it as an offload device. We get a lot better performance for a lot of our applications. I think Jim talked about this, about using NAMD or various applications, just running it directly there and not trying to send, not trying to offload matrix multiplications or anything. So far we've seen, at least for Charm++, the best performance is if you want to run on the Knight's Landing, just spawn another Charm node there that has a PE on every rank or whatever.
Okay, thanks.
So to follow up that comment, the compute per watt for accelerator cards like GPUs and the Phi is an order of magnitude better than the compute per watt for even the best power-saving CPUs that there are today. So It does add 300 watts per card, but the compute per watt goes way up. You only need to look at the Chinese Tianhe supercomputers to see this. So anyway, my question, the examples you gave where you were showing the performance as a function of the fraction of work being done on the GPUs, did you find that the critical points occurred because of the latency needed to copy data, or was it in latency in doing computation?
Oh, that is a very good question. I don't know off the top of my head. I'm pretty sure that these are a function of, this is the point at which the relative load on each of the devices is close to even, including the time it copies the data. I don't know what's the dominant factor, though, between the latency to copy or the latency to move the data both directions and actually execute it, or just the data movement versus the execution time. We didn't look at that specific breakdown, but that's something to explore further.
Okay.
So you mentioned you were doing batching of kernel launches. Are you also doing batches of pinned memory allocations?
Yes. Well, it depends. So the way it works right now basically is when the Charm program starts up, we batch like a large allocation of pinned memory we make available to the programmer. After that, no, you can still use pinned memory, and if you want to ignore our mempool, you're free to. You can even turn it off. But after the initial startup, we don't batch those pins, basically.
Let's thank our speaker one more time.